Hi. Yeah, good evening. So I hope I've started the recording. Yeah. So do you have any questions before we start? Okay. So today I plan to talk about what things to do today. Today I plan to, so this is session 10 and I plan to talk about propagators. For the Dirac field. The way we did it for scalar field earlier. Then I'll talk about gauge symmetry. I think we didn't talk about it earlier, and then we'll start discussing path integral. This is the rough plan, and from where we will take off to Feynman diagrams and so on, but which will probably not happen today. Maybe next time. Okay. So what was the Dirac field? How do we express it? We have two polarization components, one Xi1 and Xi2. If you remember the Dirac, the positive frequency solution, square root of p dot sigma bar, and this S takes two values, 1 and 2. I mean, not polarization, but spin 1 and spin up and spin down. Integration d3p over 2 pi q 1 over square root of exponential of I p dot x. Okay. So it is a linear superposition of positive frequency solution and negative frequency solutions. Then accordingly, psi bar, which is psi dagger times gamma 0, when is your exam? This exam for this particular course?
Coming 29th. So next month 29th.
Okay. The assignment problems that are being given by the course instructor, are you able to solve those? Or those are difficult?
Yes, ma'am, but I have a small doubt on that assignment.
Okay.
Last one.
Okay, you can ask them.
We can ask it later, right? We just continue those things. We can ask it in last.
Fine.
Okay, fine.
B bar is exponential minus I p dot x. Okay, so the propagator, so remember for the scalar field, time coordinate field phi, this was the propagator, phi x phi y, and this turns out to be d3p over 2 pi cube 1 over 2 EP exponential of minus I p dot x minus y. And the Feynman propagator is just the time ordered product. Time ordered product of phi x, phi y, which is defined to be so the field labeled by a time which is a later time should be to the left. I mean, you should remember that. That's a rule for this time ordering. 0, phi y, phi x. Later time should be put to the left. y0 greater than x0. And this we could write more compactly as I divided by p square minus m square exponential minus I p dot x minus y, with the contour being so we can see that this integral is having poles in the p0 plane. So this is the p0 plane. So you can see whenever p0 is equal to plus minus square root of p square plus m square, which is plus minus EP, this denominator will become 0, so the integral will diverge. So we can perform this contour integral, and we need to choose this particular contour. So here, suppose this is minus EP, this is plus EP, and the contour for that Feynman propagator has to be chosen this particular way. Do you remember the logic, or should I just briefly explain it? Why this kind of a contour will give this Feynman propagator? You remember the logic?
Yes, ma'am.
Okay. So the same thing. So what happens is when x0 greater than y0, so you need to close the contour below, and the logic is as follows. Here you have exponential of minus I p dot x minus y, which is exponential minus I EP x0 minus y0 times exponential of minus I p dot x minus y. So while choosing the contour, you should always keep in mind that at the infinity this integral should vanish, and that will only happen when x0 is greater than y0. That will only happen if you choose the contour in the lower half plane, because there your p0 will go to minus I infinity in the lower half plane. So that means if you put, so let me write it as p0. If you put p0 equal to minus I infinity here, you will get x0 minus y0. So that goes to 0, right? Because it will become exponential of minus infinity times a positive number. And when you do that, and perform this integral, P0 integral, you get back this quantity. That's the logic. And when y0 greater than y0, you need to choose the contour in the upper half plane, and similarly you perform the P0 integration. Then this pole will contribute to your contour integration, and you will get the correspondingly this propagator. Okay. Okay. Is that clear? So similarly here, so I wrote down the fields. So the propagator would be 0, psi x, psi bar y, 0, vacuum. So what is this quantity now? Let's evaluate. Putting the spinor index explicitly. This is equal to summation over S, comma R, 1 to 2, d3p prime, 2 pi to the 6, 1 over 2 square root of, let me call it q, eq, okay. Now when we, so from this, only this term will survive, because on the left we have this vacuum. So B acting on vacuum gives 0, so that gets annihilated. So B dagger acting on, this will also be 0. So that's why this term vanishes. We get contribution due to this term from psi, and from psi bar we get contribution due to this term. So that means the only two terms that survive will give AR dagger Q 0, UAS P, U bar is exponential of minus I P dot X plus I P dot Y, sorry, Q dot Y. Q dot Y. Okay. Now you can use the anti-commutation relation. Between the creation annihilation operator, which is 2 pi q delta 3 p minus q delta rs. If you substitute it there and you perform the integration over q as well as take the summation over r, so you will be left with summation over s integration d3p over 2 pi q. 2 pi cube gets cancelled out because of that factor over there, EP. Yeah, so the point is, from here you get two terms. So you need to substitute this first term, and the second term automatically vanishes because you are having annihilation operator to the right. So when the annihilation operator acts on the ground state, it becomes 0 by definition. So we are left with US A, U bar is B, to exponential of minus I p dot x minus y. Okay. Now use the completeness relation. So that gives d3p over 2 pi cube 1 over 2 ep. This is gamma mu p mu plus m ab component p dot x minus y. Okay. Likewise, if we compute 0 psi bar y b component of psi bar, e component of psi. I'm doing it just to define the Feynman propagator for the Dirac field.
Just a minute, ma'am. Last how it got that thing.
This one?
Yeah.
This using the you recall that summation over s u s p u bar s q is equal to, so summation over s square root of p dot sigma square root of p dot sigma bar then that will give us square root of p dot sigma bar p dot sigma this is equal to p dot sigma bar p dot sigma sorry, yeah, first row first column, first row second column, so p dot sigma bar what is the first term? It's m, but when we take that summation, what do we get? So summation over s sorry, dagger here. So what is this quantity? So it's 1 0 1 0 plus 0 1 0 1, which is a 2 by 2 identity. Okay, so that means this is equal to summation over s m, there is a 2 by 2 identity, p dot sigma multiplied by a 2 by 2 identity, and p dot sigma bar 2 by 2 identity m. What is this quantity? This is nothing but gamma mu p mu plus m. Remember? So what was gamma mu? Gamma mu was 0 sigma mu, sigma bar mu 0, okay, and p mu is p0 comma p vector. So gamma mu p mu identity sigma vector okay. So this is a this is M times 4x4 identity plus gamma mu p mu, which is a 4x4 matrix, which we are writing as gamma mu p mu plus M. Is this clear? Now this is what I was replacing there. So we have that, we are getting, let me paste it. So this is what we have, right? Here I'm just replacing this with this summation by that matrix, 4x4 matrix, but it's AB component because we are taking 0 psi A psi B bar Y. Is this clear?
Yes, ma'am.
Okay. Okay, so similarly we can compute this. I'm just doing it because two pi to the 6 summation over S R going from 1 to 2, 1 over 2 square root EP EQ. Now what we contribute? So psi bar is on the left, that means this will contribute, and psi is to the left, right, so this will contribute. So these two terms contribute now. So we get 0 BPS BQR dagger 0 BA that will come with Q P bar exponential of so psi B bar is coming with exponential minus I P dot Y exponential I P dot X. Okay, so similar integration and summation over R, if we take, we arrive at exponential minus I P dot, sorry, one is with Q, this one is Q, minus I P dot Y minus X. Okay, and now similar calculation if you do for V, the negative frequency spinors, then this turns out to be gamma mu B mu minus M. Okay, this you can check. We did it earlier. You can go back and see. Now this can also be written as minus del slash plus m. I'm putting this subscript x just to make sure that this derivative is with respect to x. So I just wanted to say this, that's why I did it, but otherwise it's a repetition of what we did for psi bar. Propagator exponential minus I p dot y minus x. So you can also write it this way, and this propagator psi bar this can be written as I del slash plus m. Okay, acting on d3p over 2 pi cube 1 over 2 ep exponential minus I p dot x minus y. So this minus sign is coming out because now we are taking derivative with respect to x. So when you do that, so this will act on this exponential term, and you will bring down a factor of I times p. Sorry, there is a I here. So that I times p will make it minus, and this will remain plus. So when you take this minus inside, it will become plus, and that term will become minus. That is what you have here. Okay. So the Feynman propagator is defined as, did I say that earlier? No, I said that for scalar. So the Feynman propagator.
Just a minute.
Yeah.
Here by putting p rho we denoted by 4 vector, right? But how it turns to a single direction here, from 4 direction to single direction, how it comes from this? Because this partial differentiator with slash. What is this? Rho slash, right? The last step.
Yeah.
The rho slash indicates a differentiation in x direction only, right?
Oh, okay. You are saying p mu, which is I del mu, right?
Yeah.
Yeah. So, no, but this del mu
It has been from 4 directions, it came to a single direction, right? How the transformation happens? Why the transformation happens?
Yeah. Listen. So this is not x direction and y direction. This itself is a 4 vector. This is x mu, this is y mu. It's like y minus x. How do I say that? I mean, this is a 4 vector dot product, right? So this is x mu itself a vector. So when I'm writing del x slash, I mean gamma mu del mu, but that del mu is gamma mu del x mu, but not gamma mu del y mu. When I write del slash x, I mean this. It is not like along x vector. I mean, x mu itself is a 4 vector. Yes.
Okay, now I understand.
Yeah. Okay. Yeah. Good that you asked. So the Feynman propagator is so that's why this is acting on this x 4 vector. So this will treat y mu to be just a constant. So it's y mu minus x mu. Just to be clear, let me just put that. It's p mu y mu exponential I p mu x mu. So this will act on this exponent, and it will bring I times p mu, and that I will multiply with this I, make it minus, and then you get back this matrix over there. So the Feynman propagator is defined as, call it S fx minus y. This is 0 psi x psi bar y 0. So later to the left, so x0 has to be greater than y0 for that term, and psi bar y 0 when y0 greater than x0. And just the way we could write it compactly for the scalar, we write it here as well, d4p over 2 pi to the 4. Now the propagator in the momentum space is, this is still there, but now you have that extra matrix coming from the completeness relation of those spinors, positive frequency and negative frequency, exponential of minus I p dot x minus y. Okay. And the contour remains the same for the Feynman propagator. Here you have minus EP plus EP, and the contour so you pick up the positive pole when you close the contour on the lower half plane, and pick up the negative pole when you close the contour on the upper half plane. And you have to close the contour on the lower half plane when x0 greater than y0, so that you get this propagator, and when y0 greater than x0 you will get this one, and you have to close the contour in the upper half plane. So that is the propagator. Okay. Now just to say one more thing, this propagator actually is a Green's function for the Dirac operator. So when the Dirac operator acts on this propagator, it gives a delta function. Whenever that is the case, that operator, that function becomes a Green's function of the corresponding operator. So here, if we act the Dirac operator I gamma mu del mu minus m on the propagator psi x psi bar y 0, let's say this is with respect to x, I gamma mu del mu minus m, we obtain this remove the matrix index. So this will act on this exponential term, gamma mu p mu. Sorry, I could use the compact notation, this one. So d4p over 2 pi to the 4 I gamma mu p mu plus m divided by p square minus m square. So this you already have, 2 pi to the 4 divided by p square minus m square. So when this acts on that exponential term, we get minus I p mu. So it will become gamma mu p mu minus m, exponential of minus I p dot x minus y. Okay. So, and what is that term? So that product in the numerator, it's gamma mu p mu. Let's give it a different name. Gamma sigma p sigma gamma mu p mu minus n. This is so we can write it as gamma sigma gamma mu plus whole divided by 2 and you can immediately see that this is nothing but the Clifford algebra, 2 times g sigma mu divided by 2, sorry, there will be m squared. Square terms are getting cancelled out. Okay, square terms getting cancelled out and we are left with p mu minus m square, which is exactly what you have in the denominator. So that means this particular quantity that we started with is equal to, this is equal to d4p over 2 pi to the 4 I times that entire thing becoming 1. So let me just write p square minus m square divided by p square minus m square exponential minus I p dot x minus y. So this is I times the 4-dimensional delta function. Equal to, so we call, therefore S f x minus y is Green's function for the Dirac operator. Okay, this is the Dirac operator. Okay. Now,
Ma'am, can you please scroll up?
yeah. Here, this portion.
Yeah.
Yeah.
Okay, ma'am. Okay.
Now, yeah. Let us now talk about the gauge symmetry. Okay. Are there any other questions? So gauge symmetry. So so for the Klein-Gordon field, the Lagrangian corresponding to the Klein-Gordon field, what was it? Half of real Klein-Gordon field we are talking about. No, I should talk about complex Klein-Gordon. Corresponding to the complex Klein-Gordon field, del mu phi star del mu phi minus m square phi star phi, and this Lagrangian is symmetric. This theory is symmetric. I mean, remains invariant under the following transformation. Phi going to exponential I alpha phi, where alpha, so this is a phased rotation, but where alpha is a constant, let's say, for the time being. So you can see immediately that this is a symmetry for the problem, because under this transformation Lagrangian remains same. So accordingly the equation of motion also satisfies the same, also remain invariant under this transformation. So this is a symmetry. Now suppose, so what is the conserved current corresponding to it? How do we, so under that symmetry, under that transformation, Lagrangian remains same. It doesn't even change by any total derivative or anything, because it's phi star, it's phi. So corresponding to phi star, you will get exponential minus I alpha, which will get cancelled out with exponential I alpha from phi. So Lagrangian remains the same. So how do we calculate the corresponding conserved current? The conserved current, J mu, will be del mu phi delta phi. What is delta phi? Delta phi is I times phi, and this is del mu phi star. So we can treat phi and phi star to be independent, just the way we obtain the equation of motion as well for phi as well as phi star. So the current will have contribution from phi as well as phi star. So the first term gives that, and the second term will be minus del mu phi star with an I factor coming from that delta phi, I times this. So that's J mu, conserved current corresponding to this symmetry, global phase transformation or phase rotation. I think that's correct. I think correct nomenclature, but it's global, meaning alpha doesn't depend on x, the space-time coordinates. Now suppose we want to gauge the symmetry. By gauge we mean we are making the symmetry local. Okay, that's what that gauge means. So suppose we gauge the symmetry meaning make alpha to alpha x, where x is a 4 vector again. So it depends on the space-time location. So that is, you are now looking at this particular transformation of your field phi, I alpha phi. Okay, what will happen now? So that mass term of the Lagrangian, which is m square phi star phi, will still remain m square phi star phi, but now the derivative term del mu phi, how does it transform? So this will transform as del mu plus it will become exponential I alpha phi, which is del mu phi plus another term coming from that space-time dependent phase, exponential I alpha phi. Okay, sorry, exponential I alpha is multiplied here also. So when we now perform, if we now perform del mu phi star, this will change by a factor. I mean, that will that cannot be just written as a total derivative. So in order to make this symmetry, let us introduce no longer a symmetry. So let us introduce a field, call it A mu, which under that transformation transforms as this. This we demand, okay, and define d mu phi to be del mu plus I phi. This is a definition. So now how does this d mu phi transform? So d mu phi would transform as a mu prime phi prime. What is a mu prime? A mu prime is a mu minus 1 over e del mu alpha. What is phi prime? Phi prime is phi exponential of I alpha, which depends on space-time location, phi. So now if we evaluate this, del mu, so exponential I alpha del mu phi plus I del mu alpha exponential I alpha phi plus a mu minus I del mu alpha this is multiplied by this is also multiplied by exponential I alpha phi of x. Okay, so now you see that that extra derivative that was coming due to the space-time dependent phase is now getting cancelled out, and we are left with exponential I alpha x. Let me take common from left, and this becomes a mu acting on phi of x. So what is that? Exponential I alpha d mu acting on phi, right? So you see that this derivative that we have defined has the correct transformation property that we want for the transformation, for the local or the gauge transformation, for that gauge transformation to be a symmetry, because d mu phi transforms as exponential I alpha d mu phi, which means d mu phi star would transform as exponential minus I alpha d mu phi. So if we modify the Lagrangian as d mu phi star minus m square phi star phi, then this is invariant under the gauge transformation phi becoming exponential I alpha phi. Okay, and this prescription is known as I think it is called, so d mu is called covariant derivative, unlike del mu which is the ordinary derivative. Okay, and one more thing, you notice that this A mu, this transformation property, so we have introduced a field A mu, but if we look at it carefully, this is the transformation under which the electromagnetism Lagrangian, if you remember, we introduced in one of our sessions, it was minus 1/4 f mu nu f mu nu. So this satisfies, I mean this remains invariant under A mu becoming A mu minus del mu some lambda, where call lambda in this context, lambda is alpha over E here. So this Lagrangian is symmetric under this transformation, and you understand why, right? Because f mu nu is del mu A nu minus del mu A mu. So f mu nu under A mu going to A mu minus del mu lambda, where this lambda is called a gauge parameter corresponding to this transformation. Under that transformation, f mu nu remains f mu nu. So this transformation is a symmetry for this Lagrangian of Maxwell's theory. So therefore we can write down this Lagrangian plus d mu phi star minus m square phi star phi. Okay, and this is called the scalar quantum electrodynamics. This is the Lagrangian for scalar quantum electrodynamics. And so this Lagrangian has an interaction term. So let me just write that down as well. What was d mu? Okay, so d mu phi star, what is it? This is del mu plus I E A mu phi del mu plus I E A mu phi star, which means del mu phi star plus I E A mu del mu phi star phi So the Lagrangian corresponding to scalar QED minus 1 over 4 f mu nu coming from the Maxwell's theory Lagrangian plus this is giving look at this term, this particular term that we are getting. So this A mu is coming from Maxwell's theory, so that is the corresponding vector potential that that gives you electric field and magnetic field, and this phi is the coming from the complex Klein-Gordon Lagrangian. So this term shows an interaction between this vector potential, I mean this Maxwell's field, and the complex Klein-Gordon field. Okay, and that term is nothing but, if you remember, this is nothing but J mu that we defined. For the global phase rotation. Okay, sorry, maybe this was too quick, but please ask me if you have any questions. I can repeat things. Is this clear, the concept clear, what we are doing here and how we achieved it? So, okay. But I should.
The J mu conserved current that just now we just derived, right?
Yeah. Yeah. Exactly.
But then there will be I, right?
Okay. So this I will not be there. Yeah.
Okay.
Okay, so the same thing we can do for the Dirac spinor. For Dirac spinor.
Just a minute.
Yeah.
So are you saying that this is like an interactive term that we are going to do in pi4 theory like that? So now the complex scalar field and the QCD is going to interact in such a way. Are you telling like that?
Yeah, quantum electrodynamics. Yeah, the A mu is the field corresponding to Maxwell's theory, and when we want the theory to have complex Klein-Gordon theory to have symmetry under a gauge transformation, that A mu field automatically comes in. Otherwise, this particular Lagrangian that we started with do not enjoy that symmetry property under a gauge transformation of this kind. You need to bring in a field A mu, and we are telling that this field, if it satisfies this kind of a transformation property under that gauge transformation, and we define this covariant derivative this particular way, then the complex Klein-Gordon field will be symmetric under that gauge transformation. But the price that we pay is there comes a interaction term, this one. So this is showing interaction between the Maxwell's field A mu and the complex Klein-Gordon field. Yeah, these are the things that we will study, but phi-4 theory will be different from. Yeah, phi-4 theory will be just lambda over 4 factorial phi to the power 4, this kind of an interaction. But this is also an interaction term for quantum electrodynamics. Yeah.
No, ma'am, I'm not talking about phi-4 theory.
Oh, okay. Okay, so you are just asking whether this is an interaction between the Maxwell field and complex Klein-Gordon. Sorry, what was your question?
Right. Just scroll up.
Okay.
Ma'am, can you please scroll up?
Yeah. Here?
Can you please scroll up a bit?
Okay.
That last term here. It should be that, right?
Which one? Sorry, which term are you talking about? I think
Am I audible?
some internet issue, I think.
D mu phi star.
Yes. Yeah.
In this derivation, there is a last term, right? E square a.
Oh, okay, this term. Yeah, this term is also coming, but yeah, we can keep that. I forgot to write it.
Do we miss that term?
Yeah. I just wrote it now.
Okay.
Now for Dirac spinor, so the Dirac Lagrangian psi bar I gamma mu del mu minus m psi. So you can see this also satisfies, this is also invariant under a global phase rotation where alpha do not depend on x. But if we similarly make this transformation, gauge this particular symmetry, then that derivative term will again pick up a factor due to that phase space-time dependent phase, and in the similar way we introduce the field A and write it as d mu minus m psi. This satisfies that symmetry. This remains invariant under that transformation. If we make the transformation local, then this particular Lagrangian remains invariant. So here d mu is just as before, del mu plus I e a mu psi. Okay, and the transformation property a mu remains the same, minus alpha. Okay, with this particular transformation property of the field a mu. So we can write down the QED Lagrangian minus 1 over 4 f mu nu plus psi bar I gamma mu d mu minus m psi. Now if you notice that the extra term that you are getting because of that covariant derivative. So psi bar I gamma mu del mu minus m psi, and the extra term will be minus e psi bar gamma mu psi a mu, right? And remember, this is nothing but the conserved current corresponding to this global phase rotation. So this is, as we said, that this is the symmetry of this theory. So you get the corresponding conserved charge, corresponding conserved current. To get the charge, you integrate over space the zeroth component of the current. This is what? This is I psi bar gamma mu psi. Okay, and we have that current here. Okay, so the same thing is happening like for the scalar field. When we couple to the electromagnetic Maxwell's field, we get the current. Likewise here also we get that current in the corresponding quantum electrodynamics Lagrangian. Okay, so this is all I wanted to talk about the gauge symmetry. Are there any questions, or I will proceed to discuss path integral?
Ma'am?
Yeah.
From here only the particle physics are emerging, right? From QFT.
Sorry, say that again.
From here, from this gauge symmetry, only the particle physics emerging from QFT, right?
Yeah, I mean, the heart of quantum field theory is when we discuss interaction between different fields, and yeah, from here we can see the quantum electrodynamics Lagrangian and corresponding Feynman propagator and so on. We can discuss in the interaction theory only. Yes.
Okay.
We will come back to these, but I'm just worried we have 2 more sessions. I don't know how much will be covered. What is being discussed in the lectures now? Am I doing something completely different from what is being taught in the lectures? Can you tell me?
So far in week 9, the conserved charge and symmetry generators has been covered.
Okay.
From week 10, pi 4 theory is about to start.
Okay. So, okay. And the doubt that you have, that is based on which topic?
Actually, that depends upon the conserved current that now we are discussing.
Conserved current corresponding to Dirac field and...
No, correspond to the complex scalar fields.
Okay.
Actually, that's a problem sum, but I got a different answer. But that answer, which is correct, is something different.
Yeah, before
That's
we
what.
start path integral, can you show me that doubt? Then I'll discuss path.
Just a minute, ma'am. Is it visible?
Yeah.
Yeah, actually, this is the question, the second question.
Okay. Just a moment.
So, I got the option A, but it shows option B is the right answer.
This is asking what do you get for T0I? Sorry,
Yeah.
I cannot see the entire question. Can you zoom out maybe? Huh. Okay. The summation over A runs from... Okay, that is the action.
Yep.
Sorry. Okay, that's a complex line coordinate field. Just a moment, let me write down the question and then I'll share again.
Sure.
So S of phi is d4x del mu phi star. What is A here? These are not spinors.
No, these are just scalar fields.
Oh, those many fields. Okay, A runs from 1 to n. Evaluate the energy momentum tensor for this theory. Del mu phi minus m square phi star phi, and the options. Sorry, now can you go to question 2? That I have written the question.
Yeah, this is the question too.
Yeah, so T0I, okay, you have to figure out what is T0I, which is phi star del I phi star plus pi del I phi. Which one is the correct option? Oh, that's written there. Pi star del I phi star.
Option A.
Okay, let me see. Okay, I'll share the screen, you can stop sharing.
Okay. Is it fine?
Yeah. So this is the energy momentum tensor. Okay. So how do we find the energy momentum tensor? T mu nu is del mu phi minus eta mu nu L, right? So what is L? L is Lagrangian density is this phi star phi. So T mu nu would be right. You also need to add the contribution due to phi star. So plus del L for this particular problem, phi star, we have two fields, del nu phi star. Okay, so that means T mu nu turns out to be del mu phi star del nu phi plus del mu phi del nu phi star minus eta mu nu L. So what do we get? When we subtract eta, okay, so phi star del nu phi plus del nu phi star minus eta mu nu will make the first term del mu phi star del nu phi, okay, minus will become plus eta mu nu phi star phi. So this term getting cancelled out, phi star plus eta mu nu phi star phi. Now question is asking you to find out what is T0I, right?
Yes, ma'am.
Del 0 I del I phi star, and the options are these. So del 0 phi is so for that field, what is the corresponding conjugate momentum? Phi is del L del phi dot, that will be if I want phi dot, that means it will be phi dot star so this is phi dot del I phi star. So you are getting a different answer, you are saying, right? Is it what you are getting? Pi star del I phi star plus pi del I phi?
Yeah, this is the answer.
But this is not what they are giving as a correct answer.
No, actually, this is what they gave. I made a small mistake. I missed that minus L in that formula.
Oh.
So the whole that's my mistake. So it's fine.
Then you understand now. This is the answer.
Yeah, I understand. I understand.
Oh, great.
Okay.
So let's move on to path integral. Yeah, let me know if you have any other questions on assignments, because we barely discussed assignments, kept on discussing theory. Okay. So path integral, what's the time? Okay. So let's forget for the time being fields, and let's go back to our session 1 when we were talking about some finite degrees of freedom, like QI. Consider these finite degrees of freedom QI like a quantum mechanical system. And suppose we want to compute this probability transition amplitude. Okay, how do we do that? So we insert basis states So this you might be already familiar with. Okay, and instead of inserting just one basis state, let's say we want to insert n-1 number of, so call Qi to be Q1 and Qf to be Qn. Okay, so that transition amplitude from Qi to Qf can be written as Q2 up to Qn-1 dot Qn, so Q2 Q at T2 overlap with Q1 at T1. Okay, so these are all the other inner products. So we are inserting here, we have inserted identities, but it's like we are inserting n minus 1 number of identities. Okay, and what are these amplitudes? Let's look at one of these terms. How can we write it down? So for simplicity, consider the Hamiltonian t square over 2m plus v q. Okay, and so that amplitude if we have exponential minus IH, before I look into this particular term, let me say another thing. What we ultimately want to do is take this n to infinity. What is delta t? Delta t is defined as Tn minus T1 divided by n minus 1. So in the limit n tending to infinity, what does that mean? You are as if considering all possible paths starting from q1 t1 to qn tn. If you take this particular limit n to infinity, then delta t will go to 0. Okay, and this will become, this we can write as integration over q of t times that product can be written as exponential of I over h cross s, where s is some function. We are not sure yet what that function is. As it will turn out, this s is nothing but the action that we are familiar with for Dirac Lagrangian as well as Klein-Gordon Lagrangian. So this is what we are going to show, how that product is actually exponential I over h cross times the action. So exponential, so this is what that particular term we can write as qn exponential of minus I plus ih tn minus tn minus 1 qn minus 1, right? And what is tn minus 1? That is delta t. Delta t that we defined here, same delta t. Now suppose we are considering this Hamiltonian for simplicity and we insert it in that exponent. So qn tn, this amplitude then becomes, what is exponential ih delta t? This will become t square over 2m plus vq. These are operators. Whole thing multiplied by delta t, sorry, I is outside. So this is exponential I p square over 2m delta t times exponential I V delta t, okay, times, since these are operators, there is a formula by Baker-Campbell-Hausdorff formula which says that exponential of a plus b, this becomes exponential a exponential b times exponential ab commutator divided by 2 and so on. So the next term coming from the commutator would be of order delta t square, but we said that we will take delta t to 0. So we are not worried about these terms, okay. So exponential I h delta t can be approximated as these two factors, these two terms. So suppose we substitute that in this matrix element, transition amplitude. If we do that, we get exponential of I p square over 2m delta t times exponential I v delta t qn minus 1. Now we are inserting another identity, in momentum basis, okay. So that this operator, sorry, we want to insert momentum basis, so that this operator can be replaced by Pn minus 1, the corresponding eigenvalue, exponential I Pn minus 1 square over 2m delta t plus, and this will also be evaluated at Qn minus 1 delta t, okay, and we are left with Qn minus 1 Pn minus 1 and what are these? These are the plane waves, right? Plane waves, you can, so that can be written as, so first of all, this term that we obtained, this is nothing but the Hamiltonian evaluated at Qn minus 1 Pn minus 1, right? So this is the Hamiltonian function of P and Q times delta t exponential of I okay. So therefore, let's come back to this expression. So we have these products, so and with this particular Hamiltonian we have obtained this expression for one of those terms here. So suppose we substitute those here in this expression. So what does that give us? QF TF QI TI. This will become, we already had those insertions Q2 up to Qn minus 1. Now we also require P2 up to Pn minus 1 for all those each of those terms. times exponential of I summation over I equal to 1 to n minus 1 h pi qi delta t. Let me take delta t common. If I take delta t common, then I'll get then I will get qn minus 1 times pn minus 1, sorry, qi plus 1 minus qi divided by delta t. Okay, so in the limit, okay, the entire thing multiplied by delta t. So in the limit delta t going to 0, this can be approximated as exponential of I so this is what limit delta t tending to 0, q evaluated at t plus delta t minus q evaluated at t divided by delta t, that is nothing but q dot t. So the first term gives summation over I integration over delta t pq dot plus the Hamiltonian. Sorry, there is something wrong. There should be. Just give me a minute. Yeah, I have missed a minus sign somewhere. Oh. This will be minus. Sorry about that. So all these will be minus and we get minus here. So this is pq dot minus h. Okay, fine. And this is phase space path integral because we have integration over p as well as q. But actually we can perform this integration over p if you look at this term here. This is p square and this term here is linear in p. So you can actually perform that integration. So consider just one particular term, I pi square over 2m. Okay, there is a minus, plus pi qi plus 1 minus qi. Okay, so we can complete the square. So this is dpi minus I pi square over 2m let's take m to be 1, doesn't matter. If I take that 2 common, pi square minus 2 pi qi plus 1 minus qi. dpi exponential of minus I over 2 pi square sorry, there was a delta t as well, entire thing multiplied by delta t. So suppose I am taking delta t common, so there will be this division by delta t. So 2 pi, that is qi dot, plus qi dot square divided by 2, we are adding by hand, so we need to subtract that, qi dot square by 2. So this will be some constant, and that we can absorb in the definition of the measure. So ultimately this path integral that we have expressed in this particular way can also be rewritten as integration over only the configuration space exponential I integration dt q dot square over 2 minus that v of q coming from that Hamiltonian. Okay, so v of q had, so h had one term due to p square that we have taken in order to perform that integration, and this v remains. So this becomes the exponent now, and that is nothing but the Lagrangian, right? The corresponding Lagrangian for the Hamiltonian that we have chosen. And so you can recognize this to be exponential I s, which is a functional of q. So h cross we ignored from the beginning, but if you put that, you will get a by h cross. Okay. So let me pause here and ask if there are any questions.
How can we connect this to field theory? Because this is for quantum mechanics, right?
Right. So, yeah, that is what we are going to do now. Suppose we want to obtain expectation value of any operator, okay, any operator, let's say q. So we sandwich it between qi ti, qf df. Okay, so in the path integral this will become dq. What can we do here? We can insert qf tf, this basis. So it will give with the corresponding eigenvalue for the operator q. So we have inserted a basis which is the eigenbasis for that operator q. So it gives the corresponding eigenvalue. And this is in the path integral language, I over h cross s q of t. Okay. Now suppose we want not just a single operator here, but two such operators. So
Just a minute, can you please scroll up?
yeah. So you can follow the similar procedure that we did for these. I mean, we started with only the overlap of this state with this state, and we followed that procedure to write this integral. Now we also have this extra term coming, eigenvalue coming due to this operator, and that remains in the integrand, and we get this path integral.
Okay.
So suppose now this was just one operator. Now here this is a number, eigenvalue is a number. Here it's an operator, and we have already seen in the context of deriving the propagator and so on that time ordering becomes important. So how do we keep track of that operator? So the point is, the path integral gives the time ordered product. So if we, let's say we are evaluating q at t1, q at t2, qi ti, then this is theta of t1 minus t2, qf tf, q at t1, q at t2, qi ti plus theta t2 minus t1 tf. So these are the Heaviside step function, which is non-zero only when the argument is greater than 0. So this means you get this particular term when t1 is greater than t2, and you get this particular term when t2 is greater than t1. Okay, and Feynman path integral evaluates this time ordered product only. S q. So qftf, time ordered product of qt1, qt2, this is equal to that path integral. Yeah, now as you pointed out, these are all in quantum mechanics. How do we go to the corresponding field theory? So in field theory, which we will...
Ma'am, just a minute. From the step function, how it came to this path?
Sorry, from the step function? No, this sorry. This is the definition of time ordered product.
Okay.
Yeah. So what I was now you were saying that these are all in quantum mechanics. How do we write the corresponding? What do we do with these in quantum field theory course? So the point is, we will now, so as we said in our first session, these degrees of freedom are promoted to the fields, and these labels I and so on, these are promoted to the space-time locations where we are in. So that means if we want to take now the time ordered product of let's say some Q1, Q2 and so on, or a better notation would be, let's say some fields only, phi at x1 up to phi at xn, okay. We are taking the vacuum expectation value. Then the corresponding path integral we write as d phi exponential of I is phi x1 up to phi xn, but we also divide by the just to normalize it, divide by the path integral without any insertions. Okay, so we can start from here maybe next time. And so this is how the corresponding path integral will be in quantum field theory. Is that okay, Dhanush?
Yes, ma'am. But we still don't know how we transform from here to there.
From here to here, it's because okay, right. So there is some subtlety that is going on, because you might think these were some states QI, TI, QF, TF, how we are now having vacuum to vacuum expectation value. Is that what your question?
Yeah, that's a thing. And the thing is, why now we are normalizing to 1 before we are not?
So this is a okay. So let me try to answer that. So any state psi we can write as dq psi. So now we want the vacuum to vacuum expectation value. Okay, that normalization I'm coming back. So how do we going from this any state to this vacuum state here? For that we need a trick called analytic continuation. What it does is start with any state Q at T, the states that we had here, and insert. So what is QT? It's exponential of minus I H T Q. Okay, and then we are inserting the basis states, which are the eigenstates of the Hamiltonian. So this can be written as summation over n exponential of minus I E N T. Now the analytic continuation says, if you take T2, replace T2 T times 1 minus I epsilon, where epsilon is a positive quantity, and then take T tending to infinity limit. Okay, if we do that, then this state will be projected onto the ground state. How? It is in this particular way. So okay, so that state QT, Q at time t, we can write as 0 exponential minus I E0 t plus summation over n greater than 0. Okay, now this particular limit, this particular change of time coordinate, which is called analytic continuation, will only give you this term, the first term. This is the only term that is important, because these terms are decaying faster compared to this first term. You see why that is the case? Because this is minus I times En t, where En, these are the excited states, so those are always greater than 0, and you have 1 minus I epsilon times minus I En. So neglect the first term, look at the second term, it's minus of epsilon En, right? So minus epsilon En times t is also there. Now you take t to infinity, so this term decays faster, this goes to 0 faster. So any state qt is projected onto the ground state. So when we are writing this term here, it's understood that t has been taken to t times 1 minus I epsilon, so that that state gets projected onto the ground state. I don't know how well I could explain it, but did you get the point? So should I explain it again?
No.
Okay.
So far.
Yeah. So this is in the t tending to infinity limit, and likewise, sorry, it should be minus infinity. And t tending to infinity limit means it's far future. If we take t tending to plus infinity, then the corresponding dual state will be projected onto the ground state. Exponential of I E0t. That's why this vacuum to vacuum expectation value, we could simply write corresponding q variables. We just wrote in terms of the field phi and so on. Now this normalization is also necessary just to normalize these ground states that we are having in the numerator. I guess.
But already the ground states are normalized, right?
Sorry?
Already the ground states are normalized.
Normalized. Ground states are normalized, but I think these states will, these overlaps will remain there in the numerator. That needs to get cancelled out. If we want to cancel these terms, then I think that I think that normalization is also necessary here somewhere, but I'm being a bit sketchy. I didn't write those properly, but maybe I can check a bit like how that normalization should also be incorporated in the quantum mechanical sense. But in whatever we are going to do, every time we will normalize the vacuum to vacuum expectation value of the fields, product of fields, by this path integral without any insertion.
I heard that whatever we are doing in canonical quantization, it can be done in path integral also. Is it true?
Sorry, whatever we are doing in canonical quantization
can be done in path integral too.
No, what do you mean by that?
Like exponential value, or else that Feynman propagator, those and all. So is it possible to just, because we know how to canonically quantize that Feynman propagator, can you just
we will
do
get
for
the
the scalar fit?
Feynman propagator using this path integral technique. I'll show you next time.
Okay, then it's
Feynman
fine.
propagator, yeah, exactly. The time ordered product of the expectation value of time ordered product of two fields expectation value that you obtained, that you wrote to be the Feynman propagator, that will immediately come from this path integral technique. This is exactly what I will show you next time.
Okay, then it's fine.
We will introduce the generating function and then explain the Feynman diagrams and also this Feynman propagator. Let's do that next time. Yeah. Are there any other questions? This normalization, I will check a bit where that can be incorporated in this path integral of in quantum mechanical sense also. But this is the standard definition in quantum field theory. And this vacuum has to do with this trick called analytic continuation. These are actually very useful techniques, but not so much necessary for as far as this course is concerned.
No, here also we are using the same thing for propagator.
Yes, vacuum to vacuum expectation value. Yes. Yeah. Okay, great. Let's stop here and meet next week.
Sure.